Chapter 11, Analysis of Variance. In Chapter 9, we talked about one-sample hypothesis testings. In Chapter 10, we talked about two-sample hypothesis testings. So now in Chapter 11, we're going to talk about two or more samples hypothesis testings. And in this chapter, we're specifically dealing with numerical variables. Once we get to Chapter 12, we're going to talk about 2+ sample for categorical variables. But for this chapter, for Chapter 11, Analysis of Variance, we're going to talk about 2+ sample with numerical variables. So for Analysis of Variance, or ANOVA, what we have is one-way ANOVA and two-way ANOVA. We're going to go through one-way ANOVA first, and then we're going to go through two-way ANOVA afterward. So for one-way ANOVA, what we have in the HNL is that, so for HNL, we have mu1 equals to mu2 equals to mu3 all the way to mu c. So all the mean are the same. That's what we have in the original situation. And what we want to prove is our H1. We want to prove that not all the mean are the same. So what we're proving is that at least one of the mean is different. So it could be one of them is different. So just the example that I gave you, our mean 3 is different, or it could be all three of them are different. So what we're proving is that at least one of the mean is different. And when we're dealing with ANOVA, what we're dealing with is F distributions. So F distribution is right skewed because we have a right tail. And what we're interested in is the right tail. For F distributions, we're going to use the same formula that we learned in Chapter 10 to calculate the p-value and critical value. We're going to use f.this.rt to calculate the p-value, and then we're going to use the f.imv.rt to calculate the critical value. And when you're doing the analysis for the one-way ANOVA table, this is the formula sheet that you need to refer to look at the relationship between the degree of freedom, the sum of square, the mean square, and the F. F is your F statistics.